All right, good morning, ladies and gentlemen, and welcome to Calc Review 16. This is a video where we'll cover, rate in, rate out problems. And what that means is, the way I like to think of it is it's a situation where there's just like a pile of something. It could be gravel, it could be bananas, it could be sand, it could be water. I know it's strange to think of a pile of water, but just thinking of these problems in this way helps me sort of visualize them in a simple way. So there's a pile, in this case, a pile of gravel. And there's always going to be some rate in function and some rate out function. One thing you have to be careful about is make sure that the rate in functions and the rate in function and rate out function, are they happening at the same time, or does the rate out start a little bit later? So sometimes that'll occur where the rate in is true throughout the entire time period, but the rate out only starts, after 3 hours or something like that. All right, so you need to pay attention to the time period. All right, so in this situation, we have gravel arriving at a processing plant and also gravel being processed at a processing plant. And the rate at which those two things occur determines the size of this pile of unprocessed gravel. Okay, now the rate at which unprocessed gravel arrives is given by this function. So this is your rate in. And then later on, we see that the plant is processing gravel. So this is your rate out. It's 100 tons per hour. One thing to notice is that both of these exist between the hours of 0 and 8. So rate in and rate out are both live during the entire time period. All right, so in your questions, I noticed 1C and 1D came up a lot, so I'm going to go over those. Is the amount of unprocessed gravel at the plant increasing or decreasing? So if you think of these problems again as just a pile of gravel that is either increasing or decreasing depending on rate in versus rate out, it makes it very clear that all you need to do to answer this question is just compare the rate in at time 5 and the rate out at time 5. Of course, if the rate in is greater than the rate out, then the amount of unprocessed gravel is increasing, or that pile is increasing in size. And if the opposite is true, if rate in is less than rate out, then the amount of unprocessed gravel is decreasing, or this pile size would be decreasing. So really, we're just going to set up the equation or inequality. G of 5. Well, I guess we're not really setting up an inequality, but we're just going to evaluate G of 5 to get the rate in at this particular time period. And I'm going to take a moment and do that with my calculator, since this is a calculator problem, so give me one moment. Okay, as it turns out, the rate in at T5 is 98.141, and the units are tons per hour. So at this exact instant, gravel is arriving at 98.141 tons per hour, whereas of course, rate out is constant at 100 tons per hour. All right, and as you can see, the rate out is greater than the rate in. So you'd say something along the lines of, since G of 5 is less than the rate out, the amount of unprocessed gravel is decreasing at T equals 5 hours. And that's it. All right, so it's just a simple comparison problem. Cool. Part D. Now we're looking for a maximum, the maximum amount of unprocessed gravel at the plant during the hours of operation. All right, this one is a little bit more involved. A few things. We don't actually have explicitly the function that tells us the amount of gravel at any point in time. And that is the function we're trying to maximize, right? So let's imagine what that function might look like. Let's call it A of t. So the amount of gravel in this pile at any given time t. Well, of course, since this is a pile that's sort of changing in size, we want to take into account how much gravel was there at the very beginning. And when the day started, there were 500 tons of gravel. So we need to take into account our initial condition. You can think of this as A of 0. And now that we have our initial anchored point, we can add to it the amount of gravel that was brought in. So if I have the rate of gravel coming in and I integrate that rate from t equals 0 to t equals some other time t, this gives me the net change in gravel incoming from t equals 0 to t equals t, right? And so if there was, let's ignore the rate out for a moment. If there was just gravel incoming during this time period, we would have a starting amount of 500 tons. And then this integral would give me the net change of gravel brought in. And so the total amount of gravel at any time t would be this initial starting point plus whatever was brought in. This gives you net change of gravel brought in from 0 to t. Okay, but of course there is gravel being processed, and so we do have to take that into account. And what we're going to do is take into account the amount of gravel. We're going to take the rate of gravel being processed, and we're going to integrate that rate. So that rate is constant 100. So we would integrate from 0 to t 100 dt. This will give me the net change of gravel processed from 0 to t. And I'm subtracting this term because that is decreasing the size of the pile. Every piece of gravel that is processed, this pile will shrink. All right. So that's the function we're trying to maximize. Now, how do we maximize a function? Well, the first step is to take the derivative. All right. So a prime of t is pretty simple here because we have a constant and we have two integrals, and the fundamental theorem of calculus part 2 says that the derivative of a definite integral is just basically the integrand itself, but you do need to pay attention to the limits of integration. Are they constants? Are they functions? Because that might change things slightly. But in this case, the derivatives are very simple. So a prime of t ends up just being g of t minus 100. All right, that is the derivative of the amount of gravel in this pile at any time t. Now, since, as you can see here, we're on a closed interval of time, t equals 0 to t equals 8 inclusive, this means that we have additional candidates. Not only are the critical points candidates, but so are the endpoints, and we do need to take those into account. So I'm gonna go ahead and list the table of candidates and start with 0 and 8. Those are the first two candidates for sure. What we're going to do with our derivative function is we're going to set it equal to 0 and we're going to set it to be undefined because that's going to help us identify our critical points. So let's use this to identify critical points. All right, so a prime of t equal to 0, g of t minus 100 equal to 0. This is a calculator problem, so I'm going to go ahead and simply use the calculator. Give me a moment while I do that. Okay, so using the calculator, I found that the derivative equals 0 when t equals 4.923 hours. So I'm going to add that to the list of candidates. And as far as the derivative being undefined, well, if we take a look at our function g of t, cosine is continuous for all values from negative infinity to infinity. So nothing between 0 and 8 will make it undefined. So g of t will never be undefined. The rate out is just a constant 100, so that will never be undefined. So there's never going to be a situation here where the derivative is undefined. So that is a situation we don't need to take into account. And now all we need to do with these values is determine a of 0, a of 4.923, and a of 8. And luckily, we have a pretty nice function up here that will easily give us these numbers. Now, of course, it'll be a little bit of calculator work, but the calculator does anything you need in terms of differentiating or integrating. And here, obviously, we want it to integrate. So once again, give me a moment while I use my calculator to evaluate these numbers. Just to be very clear, here's what I'll be typing into my calculator to calculate a of 4.923, let's say. So I'm going to start at my 500. I'm going to integrate the rate in. I'm going to add to it the integral of the rate in from 0 to 4.923. And I'm going to subtract the integral from 0 to 4.923 of the rate out. So this is what I'm going to plug into my calculator to get a of 4.923. And I'll do something similar for a of 8. A of 0, of course, as we know, is 500 tons. So that we can start out right away, write that in. All right, so give me a moment and I will do the other calculations. All right, welcome back. And as you can see, I filled in the table. We have 500 tons, 635.376 tons, and 525.551 tons at these particular time periods. Again, these are the only candidates for absolute maximum. And so there you have it. The absolute maximum occurs at time 4.923 hours. And it is, the absolute maximum is 635.376 tons. Let's see exactly what they were asking. So they're asking for what is the maximum amount of unprocessed gravel. So our final answer would be the maximum amount of unprocessed gravel is 635.376 tons. All right, that answers the exact question they're asking. They said, what is the maximum, not when is the maximum. All right, and the justification, of course, is this work that you see here. All right, let's do the second problem, part D. This is another one that came up. It's very similar to the problem that we sort of just talked about. But once again, this is a rate in, rate out problem. We're talking about, in this case, you can think of it as a pile of bananas. I know it's probably not literally a pile of bananas, but just think of it that way. And it makes things simple. There's a pile of bananas, and this pile, there's customers removing bananas from the display table. So this would be a rate out. It's a little tricky. They give you the rate out first, but that happens. And then they're going to be a little bit later on, employees start adding bananas to the table. So this is going to be right into the pile. The thing that I really want you to notice is that the time periods for these two functions are not exactly the same. So you have to pay attention to that. So here we have a pile of bananas. We have a rate in, and that rate in is what we're calling G of T, little g of t. and rate out, that's what we're calling f of t. All right. Again, nobody really asked questions about A, B, or C, so that's why I'm only doing part D. Part D, very similar. How many pounds of bananas are in the display table at time t equals 8? So we want the amount of bananas at any time t, and this is very similar to what we saw before. We want to take into account the initial condition, so how many bananas were there right at the onset, and we see that there are 50 pounds of bananas. Now, we want to add to that the rate in, but the rate in, remember, only begins at time 3. So we're going to say time 3 to time t of g of t dt. This would give me the net change in bananas added from t equals 3 to t equals t. And then, of course, we want to subtract the rate out, but the rate out is starting from 0. And they both go all the way to the end at 12. F of t dt. Once again, this is going to be rate out. So we're integrating rate out. So we'll get net change in bananas that were taken away from this pile from t equals 0 to t equals t. And we are interested specifically at a of 8. So we're going to do 50 plus the integral from 3 to 8 of g of t dt minus the integral from 0 to 8 of f of t dt. And once again, this is a calculator problem, so just give me a moment. Okay, and after using the calculator to evaluate this expression, you get 23.347 pounds. Now, one thing is, I remember this was on one of our class exams, and a lot of you, the question does ask, oh no, the question asks for how many pounds. Okay. I think a lot of you tried converting that to an integer for some reason, but maybe the question was worded slightly differently. But yeah, the question says how many pounds. Of course, a number of pounds does not have to be an integer, and so please don't try to convert this to an integer. This can be some decimal real number. So 23.347 pounds is the final answer. And there you have it. All right, ladies and gentlemen, I hope this was helpful for those of you that are watching. And be well. Talk to you soon.